Thank you very much, Stan, and thank you to those who have organized this wonderful event. It's really an honor to be here, and I'm looking forward to all of the other talks as well. So I will be talking about the challenges and opportunities of meeting nutrient needs during the first 1,000 days, and I don't think I need to tell this audience that this is a key window of opportunity spanning from periconception through pregnancy, the first 6 months postpartum, during which exclusive breastfeeding is recommended, and then the period from 6 to 24 months when high-quality complementary feeding is needed for the child. This window is critical because it's the age of greatest vulnerability to malnutrition and infection, leading to stunted growth and development. And this can lead to long-term physical and mental damage, as you will hear later. Now, I would like to argue that the challenges in meeting nutrient needs during this period are a long-standing dilemma, going back a very long time. I'll start with pregnancy and lactation. These are the nutrient needs of a woman in terms of the percent increase over the needs of a non-pregnant, non-lactating woman. So on the left are the values for pregnancy and on the right for lactation during the first 6 months. And the ones in red are those where the increase is more than 50%. So during pregnancy, you can see there's a very large increase in requirements for protein, folate, and on the right, iron. But the needs are even greater during lactation. You can see the increases of greater than 50% for protein, vitamin A, vitamin C, vitamin B6, iodine, and zinc. And then you may notice the negative 50 for iron, and that's because women actually have lower iron requirements if they're not menstruating during the first 6 months postpartum. But the point is that the needs are vastly greater than during the non-pregnant, non-lactating period, even though energy requirements are not that much higher. The first one shows only 13% higher during pregnancy and 25% during lactation. So women need a nutrient-rich diet. Now for the baby, the same thing is true during the period of complementary feeding from 6 to 24 months. Children at that age don't eat very much, but they have very high nutrient needs for growth and development. So the foods that they consume have to be very high in what we call nutrient density, and that's the amount per 100 calories. So just to illustrate how this looks compared to an adult male, this is the amount of food that an American male might eat if their requirement is 2,800 calories. Not a very nutritious diet, but these are the photos we could find on the web. So that's 2,800 calories, and then for a baby who's 6 to 8 months and breastfed, that is how many calories they would need from complementary foods, only around 200 calories. That's not much food, but their nutrient needs are very high. So when you calculate the amount of nutrient per 100 calories that they require, you can see that it's quite high, especially for iron and zinc. In this slide on the left is for iron. You can see that the needs are greatest at 6 to 8 months, and then go down with age as their growth rate slows down. And the needs are also very high for zinc, though not quite as high as for iron. Now, when you compare the needs of a baby to the needs of an adult male, per 100 calories, the baby needs much higher nutrient density. In this slide, you can see this for a number of different vitamins. The baby's nutrient density is in blue, and the adult male requirements on the right in red. And the same is true for a number of minerals shown here. Vastly higher nutrient density required, especially for iron, where you can see that the requirement is 9 times greater for the baby in terms of nutrient density. So when we look at complementary food diets around the world, we often find what we call problem nutrients, very hard to obtain the amount needed. That's particularly true for iron and zinc, but other nutrients may be low depending on the types of foods consumed or the water or soil content. And even when you use a best-case scenario with the foods available to families, for example, in this one study in Guatemala, they were not able to come up with a diet that would meet all the needs for the baby. And even improved complementary food recipes are usually not quite high enough in some of these problem nutrients. And when we use linear programming techniques to try to create diets from unfortified foods, we also run into challenges. As shown here, when we put together a diet for a baby of complementary foods that is 5 food groups that has grain, legume, green leafy vegetable, egg, and either fish or chicken, we're not able to even come close to the amount of iron that they would require. You can see here only about 30% of bioavailable iron is provided, and it also falls short for zinc. That's at 6 to 8 months. This was in 3 different countries where we modeled the local diets consumed in those places. And the same is true at 9 to 11 months, particularly for iron. The situation becomes a little bit better for zinc at that age. Now, this leads me to say that a heavy reliance on a cereal-based diet is really not ideal for infants and young children for a number of reasons. First of all, porridges out of grains usually have low caloric density, and sometimes that's too bulky for the small stomach size of a baby. In addition, cereal-based diets are low in many key nutrients, and they have high levels of what we call anti-nutrients, such as phytate, which binds iron and zinc and limits the utilization of phosphorus. Now, until about 10,000 years ago, at the time of the agricultural revolution, cereals were not commonly consumed by humans, and dietary quality was actually better than in modern-day diets. If you look here at the type of diets consumed during the pre-agricultural era, they tended to be very high in animal protein. This was coming from wild game and fish and shellfish and insects. Pretty high in fat, actually, with a very nice ratio of omega-3 to omega-6 fatty acids. None to minimal cereals, very high in fruits and vegetables, and almost no refined sugars, except for honey. If you contrast that with the modern diet on the right, it's the opposite in nearly all respects in low-income countries, with a very large percentage of energy coming from cereal grains. And at the same time, we know that widespread stunting of humans accompanied the introduction of agriculture. The height of prehistoric humans was actually similar to that of current well-nourished populations, and it began to decline after the introduction of agriculture in many prehistoric societies. Now, height has then increased in industrialized countries in the past 100 to 200 years due to improved nutrition and less infectious disease. But child stunting remains very common in low-income countries. So what did pre-agricultural humans consume? There actually is a hypothetical pre-agricultural diet that was put together as a composite from the types of foods consumed at that time by paleoanthropologists. It assumes 35% of energy from animal source foods and 65% from plant sources. And then they took the types of animal source foods that would have consumed and the plant source foods from wild plants, put together this composite diet, and they can calculate the hypothetical nutrient content of that diet. So what I did was to compare the nutrients from the pre-agricultural diet to the US diet here. This is from a paper by Boyd Eaton. In the blue is the pre-agricultural diet. You can see for these 4 vitamins, it's much higher than the US diet in vitamin A, C, E, and riboflavin. And the same thing is true for the minerals here. You can see very large differences, particularly for potassium, iron, and zinc. So what we can then do is estimate how the diets of people today might compare to the pre-agricultural diet. So I've done that for the diets of women in 4 low-income countries, data coming from the Women's Dietary Diversity Project. And I'll just run quickly through what this shows. The first set of bars are the minimum target nutrient densities that women would need to meet their needs at the age of 19 to 30. The red are the actual mean nutrient densities of diets consumed by women in those 4 countries. You can see that for most of these nutrients, the red bar is lower than the blue bar. So they're not meeting their nutrient density requirements, with a couple of exceptions here for vitamin A, vitamin C, and zinc. Then if you plot what the pre-agricultural diet looks like in terms of nutrient density, it's much higher than what they are eating in those countries, and higher by a large amount than the minimum target nutrient density, with the exception of folate. So this tells us that pre-agricultural humans actually were eating pretty well So what were their babies eating? Well, they were most likely eating, of course, breast milk, but also pre-masticated or pre-chewed foods that their mothers would give to them, which probably reflected the diets of the mother, including a high proportion of animal source foods. So the nutrient density of the diets of these babies was probably quite high. So if you then estimate what they would have gotten from those diets for iron and zinc, I'll show you what that looks like. First of all, at 9 to 11 months, the amount of iron a baby gets from breast milk is very low, and that's because breast milk is actually quite low in iron. And there are probably good reasons for that. And if you add in the typical complementary foods that babies consume, along with breast milk, they're only meeting 35% of the recommended intake. If you add in the iron from a diverse diet, such as I showed you earlier, they're still only up to 53%. But if they were eating a pre-agricultural diet provided in pre-masticated foods by their mother, they would be meeting 98% of their iron needs. For zinc, the situation is similar, not much coming from breast milk, up to about 50% with typical foods, a little bit better with the diverse diet that I showed you before, and well above the required level with the pre-agricultural diet. If you do that for the other nutrients, you find a similar story for calcium, magnesium, potassium, vitamin A, vitamin C, etc. So the diet was much more nutrient rich. But we're not going to go back to a pre-agricultural diet globally. Our requirements are being met by cereal grains in many, many parts of the world for a large percentage of the calories. So we need to get more creative about how we can meet nutrient requirements during the first 1,000 days. For pregnant lactating women, of course, dietary diversification and selection of nutrient-rich foods is our first choice, but we often find it difficult to meet iron needs during pregnancy, and access and cost are often barriers. So fortification and biofortification of staple foods is one strategy, and that can work quite well for certain nutrients. There are also multiple micronutrient supplements which have shown improvement in pregnancy outcomes in many places. And lastly, fortified foods or supplements with both micro and macronutrients, which can provide both essential fatty acids and high-quality protein in addition to the micronutrients. I wanted to illustrate to you a recent study published last year showing the really huge problem of affordability of nutrient-rich diets. This had to do with the consumption of fruits and vegetables across 18 countries, and it was plotted by income level. So on the right-hand side is the information for the lowest income countries, and on the bottom you can see the proportion who are unable to afford 3 servings of vegetables and 2 servings of fruit per day. In the rural low-income settings, it's about 70%, and in the urban settings, about 40%, who cannot afford that desired amount of fruits and vegetables. So no matter how good our advice is to women and their families, they may not be able to follow it. We did a similar sort of exercise in Burkina Faso using linear programming, and we found that when we tried to create diets based on locally available foods, and I won't go into all of the details here, we really couldn't meet their needs when we included only the commonly consumed foods. But when we allowed all of the foods, including rare foods that are closer to what we ate as pre-agricultural humans, we were able to meet their needs. And you see in bold there some of the foods that had to be included in fairly large amounts: sesame seeds, baobab leaves, and African locust bean. They're there, but they're just not being consumed very much. So we need strategies to increase consistently the availability, economic access, and demand for those types of local foods. So for breastfed infants and children, we have similar issues. We always try to promote dietary diversification, but again, it's challenging to meet certain nutrient needs, especially iron, and access and cost are barriers. So fortified products have become a key strategy in many parts of the world, including fortified blended foods, and home fortification, which includes micronutrient powders pioneered by Dr. Slotkin, as well as other types of supplements that are small in quantity but fortified, such as small quantity lipid-based nutrient supplements. And if I have time, how much time do I have?
Okay.
Good. I'll just give you one example of what we might expect to achieve using some of these approaches, and I'll give you an example from one of our trials completed recently in Bangladesh, which used home fortification approaches in the first 1,000 days to prevent maternal and child undernutrition. This was called the Rang Din Nutrition Study, funded by USAID. This was a cluster randomized effectiveness trial within a community-based program run by LAM through their Community Health and Development Program. And in this case, the clusters were the work area of the community health workers. The intervention itself was delivered by LAM, but the evaluation team was separate from the program staff. There were 4 arms in the trial with 64 clusters randomly assigned to each of them. In the top cluster, the women received small quantity lipid-based nutrient supplements during pregnancy in the first 6 months postpartum, and their babies received a similar version from 6 to 24 months. In the second arm, the mothers received iron and folic acid, and the baby received LNS. In the third arm, the mother received iron and folic acid, and the baby received micronutrient powder. And in the last arm, the control arm, the mothers received iron and folic acid, and the babies did not receive any supplements. There were about 4,000 pregnant women enrolled in the trial. I won't give you all the results. We have published them recently. We found a significant impact of the maternal LNS on birth size, including reduced newborn stunting and small head size. We found also a significant impact of both LNS during pregnancy and for the child on child growth at 18 to 24 months of age, and a significant impact of both LNS and the micronutrient powder on child development at 18 to 24 months of age. So just to summarize, what I've tried to communicate is that meeting nutrient needs during the first 1,000 days is a global challenge because these target groups need diets with very high micronutrient density. And in low-income populations, their intakes are well below the recommended amounts for several key nutrients because their diets are dominated by staple foods with low nutrient density and poor mineral bioavailability. And these gaps in nutrient adequacy probably date back to the agricultural revolution around 10,000 years ago. And we estimate that nutrient intakes prior to that were much higher than they are today. And for modern cereal-based diets, it is difficult to meet certain nutrient needs without fortified products due to the high cost of nutrient-rich foods. But this challenge can be met, and we have a number of different options for filling the nutrient gaps, both short-term and long-term. And it may be the case that greater impact can be obtained by integrating those types of nutrient interventions with prevention and control of pre- and postnatal infection and inflammation, and care for women and children and stimulation of early child development. So interventions that meet that challenge are likely to be a wise investment, as I'm sure that our subsequent speakers will communicate to you. Thank you very much for your attention.
So this morning we're going to talk about child development for the next 20 minutes or so. Almost everything that I will be talking about is included in the site noted at the bottom of the slide. Early child development extends from birth through age 8. That's the traditional definition. It's now been extended to conception and preconception. And there are various stages. So the first 1,000 days, as you know, is from conception through age 2. And the second 1,000 days is from 2 through 5. We see tremendous growth that happens during that time. When we look at children's development, we also see that children are growing in other ways other than physical growth in terms of their motor development, language, and so on. So it's a tremendously moving period of development. The Lancet has published 3 series on child development in low and middle income countries in 2007, in 2011, and in 2017. During that time, there has been tremendous growth in the area of child development in terms of scientific publications, funding, although not enough, adoption of policies, and global support for early child development. So we now see people from a whole variety of backgrounds, including economics, ethics, and so on, who are interested in early development. So I'm going to talk some about the 2017 series in child development, and I guess we would say what's new. So we will talk some about the science that is new, some about the policies that are new, and what we have learned is that there are 249 million children under the age of 5 who are at risk of not reaching their developmental potential. So it's certainly a topic that merits our attention. If we start by looking at early brain development during the first 1,000 days, you can see that it begins at conception, and brain development starts prior to birth. There may be elements that are prior to conception as well. And then I've drawn a box around the first 1,000 days, and you can see the phenomenal development that happens in the visual and auditory cortex as children are learning to see and hear and process. It's important to recognize that these are sensitive, what are known as sensitive periods. So the development happens at this point in time, not later. When I show this slide, I always ask people to put themselves on the slide and think about what's going on in your brains right now, in our brains. When you find yourself, it's way out at the end. Some of us are further out at the end than others. What we have learned is that the environment influences the genetic blueprint throughout, beginning probably prior to conception and then continuing throughout. You will hear more about this subsequently in the symposium. So the influences then stay throughout life. What is important is to consider the timing and the quality of the early environment and how they shape a child's potential future. This is a diagram of a life course perspective to child development. You can see it starts early on and then continues to build. It builds up through childhood and adolescence into adulthood and then into the next generation. So what happens if something goes awry with this perspective is that one goes off course, and then the risk for chronic health problems, limited economic potential, and into the next generation, this is representing a stunted child, increase. But what I'm going to do is to show you 4 trials done in the area of child development that provide the evidence that allows us to come up with a portrayal that looks like this. The first study that I'll describe took place in the US in the 70s. It's referred to as the Abecedarian trial, and that Abecedarian means early learning. This was a study that was done to evaluate the impact of a very comprehensive early child care center, early child care program. Children were recruited who were at risk. This was done in North Carolina. And then they were randomized either to participate in this center for 5 years, where they received the kind of nutrition that Dr. Dewey talked about, along with health care and a learning curriculum, or they received care as usual, which meant they were at home. They were followed through adulthood, and one saw benefits on their academic performance and on their economics in the workplace. This is a very well-known trial in the child development literature. At age 35, the sample was studied again, and let's see what they found. Oh my. At this point, they're finding impact on blood pressure, on hypertension, and on the metabolic syndrome. You can see the significant differences and the clear benefit of those children who were randomized to the treatment. Well, this was a study that was designed to look at academic performance, not to look at health. So if you look back, we see at 35 the beneficial effects on health indices. So if we look back, and this is stronger among the males and females, to data that we have from when they were very young, the data on the bottom, the growth on the bottom represents the children in the treatment arm. On the top, it represents the children in the control arm, and this is the complementary feeding time that Dr. Dewey talked about. So the complementary feeding of the children who were not receiving the treatment, they grew faster than one might expect. So this illustrates early in life that these changes begin to occur, and this was differences in weight gain. The second study that I'll tell you about briefly is the Bucharest Early Intervention Project. This study took place in Romania, where there were children who were placed in an orphanage in an institution at birth. This happened in the 90s. And then there was a randomized trial where children were either placed into a high-quality foster care or they remained in the orphanage, in the institution. So those are the foster care group, the care as usual group, and then they recruited a never institutionalized group. These children were then have been followed over time. So I'll show you two data points. This study is still going on. So the first one is these are studied by neuroscientists. So if you look at the children's gray matter when they were age 8, and so that's the neurons associated with processing and cognition, what you can see is that the children who had been in the orphanage or institution, whether they were placed in a high-quality foster care or not, have less cortical gray matter. So that would suggest that institutionalization disrupts early brain development, and that the foster care children did not have catch-up in gray matter. If we look at white matter, we see a slightly different story, where you can see the middle group is the foster care group, and you see that it's lower. Basically, you see a step progression. So there we see that institutionalization, it suggests that it disrupts brain development, but in the foster care, there's some catch-up in terms of the white matter. So that's the myelin, the processing speed. As I said, these children continued to be studied, and they were placed in the foster care, or when the study was done, the average age of the children was 21 months. So if we look at those who were placed into foster care, and we separate them into those who were younger or within the first 1,000 days, or older, that means slightly beyond the first 1,000 days, although still in the age 2, then we see that stress reactivity differs. It is as expected for the children who are younger, placed in the first 1,000 days, and it is blunted or not as responsive for children who are beyond that, suggesting that the HPA axis was disrupted for the older children. Again, this is providing more support for what occurs during the first 1,000 days, stays with us, and reprograms our ability to process information and the kinds of events that we are experiencing. The third study that I'll tell you about briefly is one that took place in 3 countries. It's an intervention among children with birth asphyxia. These children were recruited at 12 months and studied at 12 and 36 months, and there was a randomized trial of an intervention a developmentally oriented intervention in between. These are the data. The way you read this is that the bottom two lines refer to children who were in low-resource families, the top two in high-resource families, and the dotted lines represent the intervention. So you'll see that in the high-resource families, there's no effect of the intervention. All the children are improving. But here we see the intervention among the children in low-resource families, and they benefited. So what we learn from this is the low-resource families experience the greatest benefits. Okay, so this is what happened in the birth asphyxia. And by the time the study ended, there was no difference between the children in low-resource families who received the intervention and the children in the high-resource families. So you prevented disparities in this. So the intervention can alter the trajectories of the children's development, but among the children in the low-resource families. The fourth study is the one that we've done in India. These are children who are 40% stunted, 48% anemic. And this study took place in the second 1,000 days. I include it just to illustrate that while the emphasis is on the first 1,000 days, the door's not closed. So there are still things one can do in the second 1,000 days. This you read this in a similar way. The bottom two lines represent children. This time they're in low-quality schools. The top two represent high-quality schools, and the dotted line represents those randomized to the intervention. And again, what we see is that the impact of the intervention is on children in the low-quality schools. They experience the greatest benefits. This just portrays it again. The impact was on the children in the low-quality schools. And again, you reduced disparities. At the end, they did not differ from the children in, this is expressive language, in the high-quality schools. So what do we learn from these studies? Basically, there are two primary things we learn in terms of timing, that there can be a long-term impact of interventions in the first 1,000 days, sometimes extensions to interventions in the second 1,000 days, that there's both vulnerability and protective effects that happen in that first 1,000 days. It's a fluid period. So there can be negative things, there can be positive things. And we also learn to look at context, or to look at the quality, so that the impact of interventions can vary by the context. Reaching the most vulnerable can reduce disparities. So those are lessons that we learn from these interventions. In the Lancet series that I referred to, we discussed what we called nurturing care. This is what children need, not only during those first 1,000 days, but especially during that time. They need nutrition, health care, responsive caregiving, protection from danger, and opportunities to explore. These 5 domains are, each one is necessary, but no single domain is sufficient. They depend on one another, and children require all of them, not just one. Looking at them briefly, you've heard an eloquent talk about nutrition. It includes food security, focusing on conception, pregnancy, breastfeeding, complementary feeding. If we look at health, there are many interventions in health that have benefit to children's development. When we think about nurturing care, we often think about beginning in the health sector and then bridging to other sectors. If we think about responsive caregiving, that means the back and forth, the emotional development that children have. So it represents listening to children and responding to children. It's a back and forth, serve and return kinds of process. Consistent, predictable routines, sleeping here, eating here, having predictable routines. And feedback, guidance, but not harsh. If we think about early learning, those are opportunities to play, opportunities to explore, and to have multiple opportunities. When we think about protection, that means things like birth registration and children's rights. It means financial security. It means protection from violence and protection from toxins. When you put nurturing care together, it needs a supportive environment, and that supportive environment starts at home, and that includes all of the domains that we have described. But for it to happen at home, you need a supportive environment to enable families to succeed and to provide these 5 domains. So they're supported by intervention programs, and then ultimately they're supported by national policies that support these programs. If we think about platforms to reach children in the first 1,000 days and early in life, this portrayal illustrates that the health system is very involved from conception through birth, and then it continues to be involved, but it slows down a bit, and the educational system starts to be involved heavily at 5 or so, and then continues to increase. But there's a gap in between. Single sector programs often have gaps. So what are needed are multiple sector collaborations, which can be through social protection or early child care and education, to bring health and education together so that we can succeed in the nurturing care. There are many advantages. These are integrated services, meaning one service provider doing multiple tasks, and there are many advantages, often in the same location. Health and nutrition reach young children. So there are many advantages to integrated services, but there are also some challenges in terms of organization and training, so it's not a simple solution. These are some of the issues that are being addressed in global health and global child development today. Moving along, what if we do nothing? What if we continue as we are today? What if we accept that the 249 million children at risk of not reaching their developmental potential? What does that cost us? What the economists tell us that will cost us is based on the grade deficit that they will not be able to achieve, the income loss, and it results in 26% of the average adult income lost by doing nothing. So it certainly is a call to action. As a final note, I'll mention the Sustainable Development Goals that include aspects of early development. These goals are universal. They're for us to look after all of us, all 7 billion of us. It requires healthy, productive citizens to advance in the science and technology that is necessary. We need healthy kids. We all need healthy kids. So what are some features of large-scale programs to enable us to have healthy kids? Well, we need to be concerned about poverty and science, but we need a political commitment to be able to move forward. So I thank you very much, and I look forward to the rest of the symposium.
Thank you to the Gairdner Foundation for inviting me, and to the Centre for Global Child Health. I accepted because of Cesar. Today I'm talking about improving outcomes for children who experience linear growth retardation or stunting. And as you've heard from Maureen's talk, it's a well-established predictor of poor child development, and is actually one of the proxies that's used to come up with the 249 million children figure that Maureen referred to. So that if we combine the numbers of children who are currently experiencing stunting as well as those living in extreme poverty, then that estimate comes up to 249 million children. So the evidence that stunting was associated with poor child development began to accumulate in the 1980s, and that followed on from the distinctions that were made in the late 1970s by John Waterlow and others between different types of malnutrition in terms of stunting and wasting. So in 1986, we began an efficacy trial to see whether we could improve the outcomes for stunted children who clearly were at poor risk of developing badly. And we conducted an efficacy trial to look at the benefits of a home visit stimulation intervention to improve their outcomes. And this intervention had been developed in Jamaica by Sally McGregor and had shown benefits for severely malnourished children. And we were also interested that since the children were stunted, would supplementation have benefits for their development? And if we gave them both interventions, would the stimulation intervention have better effects because we were also giving supplementation? So we did a house-to-house survey of several poor neighborhoods in Kingston and randomized the eligible stunted children we identified to a control group, a group that received supplementation, and a group receiving the stimulation, and of course a group receiving both interventions. We also recruited and followed a group of non-stunted children from the same neighborhoods because we were interested in how children from the similar poor backgrounds who didn't experience stunting were developing. All children were visited weekly by a community health worker and received medical care upon request. This was if the community health worker had a concern or the parent had a concern. They could see the project doctor. The supplementation comprised 1 kilogram milk-based formula, which was delivered to the home weekly by the community health worker, as well as additional food for the rest of the family in an effort to try and prevent sharing. The stimulation, I'll talk a little bit more about in a minute, but it involved weekly play sessions conducted at home by the community health worker. There was a group, obviously, that received both, and the control group received the health care only. And both interventions were provided weekly for 2 years. The stimulation program does much of what Maureen described in terms of responsive caregiving and opportunities to learn. It was a weekly 1-hour home visit by the community health worker where she conducted a play session with the mother and the child. And the goal was really to work with the mother to improve her ability to promote development through play. It was an interactive approach with demonstration by the community health worker, practice by the mother, review of the activities that they should continue during the week, and a lot of praise and encouragement for the mother to do so. The program uses a structured curriculum, so that provides the community health worker with guidance as to what to do, what activities to do in each visit. And in each visit, the activities would teach concepts which are taught using homemade toys, songs and games, and language activities. And there's a lot of focus on those key aspects in terms of enhancing maternal-child interaction, so that responsive caregiving, listening and paying attention to the child's interests and responding. Emphasis on language, a lot of emphasis on praise and positive reinforcement, not just for the child, but a lot also for the mother, and positive feedback for the mother, and discouragement of physical punishment. So, and it really, the program really works because the mother changes. So the real goal is really to provide the mother with new skills and capacities. So to look at the impact of the trial, this is first the impact of supplementation on dietary intake and growth. Supplementation led to a fairly small net increase in intake, just about 14% of the amount of supplement provided. This doesn't mean that that's the amount of the supplement that the child ate. The child often would have eaten more of the supplement, but that it displaced some other foods that they were eating. So that it may have had a bigger effect on the quality of the diet. There was a small gain in height, with most of the benefit for growth happening in the first 6 months of the 2 years. And there were also some small gains for weight and head circumference. in this slide, that now shows the benefits for the development of the children. The top dashed line is the non-stunted comparison group. And you can see at the beginning of the trial, when the children were about 1 to 2 years old, there's already a gap in development. And if you look at the pink control group, you can see that that gap widens over the course of the trial. So one of the things I wanted to point out here is, as you also again heard Maureen allude to, that the first 1,000 days are critical for development, but it's not just the first 1,000 days, because by the end of the trial, the children are 3 to 4 years old. So you can see that the gap is increasing and the benefits are occurring during that later period. There were benefits from supplementation, benefits from stimulation, and the group that received both interventions were comparable to the non-stunted group by the end of the 2-year trial. So the benefits of the interventions were additive. We followed these children up through childhood and adolescence, and at age 7, there were no sustained benefits to growth. Within this cohort and in our setting, there was an overall trend of catch-up growth in all children, so that by age 7, while the children who had been stunted were significantly shorter than the non-stunted group, they had made substantial catch-up in height, and would now not have, at their height at age 7, would no longer, many of them would no longer have been classified as stunted. Follow-up in childhood and adolescence showed that the benefits from supplementation for development faded, but that the benefits from stimulation were sustained for cognition, and over time, those benefits spread to other areas, such as education and psychological functioning. The most recent follow-up that we've conducted with this cohort was at age 22 years, when we located 105 of 127 stunted participants who'd completed the trial and 65 of the non-stunted participants. And for the first time in this study, we were able to include participants resident in Jamaica, as well as participants who had migrated out of Jamaica, most of whom have migrated either to the US or to the United Kingdom, with a few, one or two in Canada. The measurements included IQ, educational achievement, mental health, behavior, and income. And we used a weighted multivariate analysis to adjust for the loss to follow-up, and also we adjusted for the fact that we had multiple outcomes. And this is the same child at age 22. So first to look at the long-term benefits to IQ, and what we've done here is that because there have been no sustained benefits from supplementation, we've collapsed the 4 stunted groups. So the line at the top is the non-stunted comparison group. The red line is the stunted groups that receive stimulation, so those that got stimulation only or got both interventions. And the blue line is the stunted children who were either in the control group or got supplementation only. And you can see the initial gains from the intervention. So the first two positions are the beginning and end of the trial. And then for some, the stunted group that doesn't get stimulation remains low and well below the non-stunted group. And the stunted group that got the intervention kind of levels off halfway between, so with significant gains compared to those children who did not get the intervention. They also had benefits to their education. At age 22, when we tested them, they had better achievement in reading, maths, and general knowledge. They had a significant increase in the grade level they achieved in school of 0.5 of a grade, which studies elsewhere suggest is associated with increased adult income. They obtained more secondary level examination passes, and they were less likely to have been expelled from school. And this also links back to something we found at age 17, which was that they were less likely to drop out of school. There were improvements in mental health in that they had fewer symptoms of depression and less social inhibition, although at this age we found no effects on anxiety, which we had found at age 17. Very importantly for Jamaica and for many other countries, we found a reduction in violent behavior. So children who'd participated in the intervention were less likely to have participated in physical fights or to have participated in something that we would have classified as being violent crime. So these included having fought with a weapon, hurt someone with a weapon, and these were weapons other than guns, to carry a gun or threaten someone with a gun, to have shot someone with a gun, or to have been a gang member. However, there was no effect on some of the other important risk behaviors. There was no impact on whether they used alcohol or drugs, unprotected sex, and the rates of teenage pregnancy were similar. This was the first time that we were able to look at the impact of the intervention on income. And what we did was to look at the benefits that were for the average monthly income since the participant joined the labor market. So the total amount of time in the labor market would have varied from participant to participants. Those who stayed in school longer may have joined the labor market later. So we looked at average monthly income since they joined the labor market. And we found that a 25% higher average lifetime monthly earning in the intervention group compared with those stunted children who did not receive the intervention. And these benefits were robust to many checks, including we omitted the migrants to see whether they were the ones really driving the benefits, and varying the type of employment that we looked at. So we looked at it with any type of employment, including part-time, full-time only, or non-temporary full-time employment. And the benefits have been robust across all of those types of sensitivity analysis. Another important analysis that we've done is catch-up analysis. So the gap in income between the non-stunted comparison group and the stunted control group, so those children who didn't get the intervention, is approximately 23%. And it's interesting that this is quite similar to the figure that Maureen presented as the gap that we could expect if we did nothing in adult income. But what we found is that there's now no longer a difference in income between the non-stunted comparison group and those children who received the intervention. So they've pretty much almost caught up in income at that age. And the non-stunted group is similar in their income and employment to a representative sample of the age cohort from the Jamaica Labour Force Survey. So this is also a very important gain, because while we've seen that the gaps have remained in IQ and to some extent education, they seem to have been able to almost completely close the income gap. So this is the most comprehensive evidence from a low and middle income country of the life course gains from early childhood stimulation interventions. And these benefits to education and income really are suggestive of potential benefits for the next generation of children. So the work that we're doing now is we're just completing, in fact, the 30-year follow-up of the cohort. And we've actually broadened the measurements in this follow-up. So they do include, obviously, IQ and education and attainment, but we're also looking at executive function. In terms of socioeconomic well-being, this includes income, but we're also looking at things like their saving, whether they save, their housing, other issues related to quality of life. Behavior, again, including violence. Some non-cognitive skills, which may be very critical for success, such as grit. And again, mental health. And this time we're also including some of the intermediary markers for cardiovascular disease, such as blood pressure, glucose, and obesity. The other thing that we've done is to establish a second-generation cohort. So these are the children of the participants in the original trial. And they are being tested at ages 1, 3, and 6 years. And we have some findings comparing, at this stage, comparing the children of the non-stunted participants with the stunted participants. So first of all, the children born to a stunted participant had lower height for age, with a difference of 0.6 of a standard deviation. But very few of them are actually stunted. So the deficit in height remains, but the there were just a very few who were actually stunted. So they're not, the next generation are by and large not stunted. I'm just going to move on to the next slide and come back to this one, which shows the analysis comparing the non-stunted children with children born to stunted parents who did not receive the intervention. And what you see here is that, and we were quite amazed by this, but there is a continuing deficit in development. So by and large, these children themselves have not become stunted, but they continue to have a deficit in development compared to children born to parents who were never stunted in early childhood. And while you can see that the differences are significant for overall development and cognition only, the trend is similar across all domains of development. So this is the first time, we believe this is the first time this has been shown, but we're really anxious for this finding to be replicated because it's such an important finding if this is the case, that not only are the children currently stunted affected, but their children are likely to be affected. And we do plan to, as we accumulate more children, to evaluate the impact of the early intervention. So just to wrap up with the implications of the work, the Jamaica home visit intervention has wide-ranging benefits, and these are likely to facilitate functioning in everyday life and to have led to gains in income. The intervention has been adapted and used in several other low and middle income countries, and also similar parent-child focus interventions have been done. And these have all shown significant gains in child development. So we know that this works. And that beyond stunted children, who are obviously a high-risk group, benefits are likely for large numbers of children currently not reaching their developmental potential. The gaps remaining, however, in IQ and educational achievement compared to children who were non-stunted, and the intergenerational impact on development reinforces the need for us to put a lot of emphasis on prevention of stunting as going forward, and not so. This work is optimistic in terms of showing that you can improve outcomes for the children currently stunted, but we do have to put a lot of emphasis into prevention.
Good morning, everyone. I want to thank Dr. Slotkin and the Gairdner Foundation for inviting me to come to Toronto. It's always a pleasure to be here, and it's a real honor to be part of this exciting symposium. And I want to thank the previous three speakers because they made my job very easy by really beautifully setting the stage to what I want to discuss with you today, which is really how are all these different environments that we heard about, whether it's nutritional or environmental, getting under the skin to affect health and behavior across the lifespan. And epigenetics really has emerged as one of the key biological mechanisms or substrates to explain this. So what I'd like to do today is just to briefly share with you how and the data that have led to the ideas that epigenetics really is a crucial component at the interface of our genome and our environments, and then illustrate this with some examples from our own work that speak to the fact that there is indeed a biological embedding of these early life experiences that can stick with us in many cases for the rest of our life, and touch upon very briefly on neurodevelopmental disorders, such as particularly fetal alcohol spectrum disorders, and how that might be linked to epigenetic mechanisms, and close up and how we can in turn use this new knowledge to perhaps affect public policy. So epigenetics, there are many different definitions. I actually hate definitions, but for those of you who like, you can read the one that is most commonly used up there. The particular area that we're really most excited about is social epigenetics, and that is the idea to understand the processes by which early life experiences influence the ways our genes are expressed. And so the paradigm that we are operating under is really that there are these experiences that we heard about in these beautiful lectures earlier that somehow affect biological pathways and drill all the way down into the level of gene expression. Of course, this is not a one-way road, because you can easily then imagine that this also goes the other way around. Now, the secret to understanding epigenetics is really at the bottom here, is this little piece of DNA, which actually doesn't occur like this in our cell. Instead, it's packaged in a multitude of different components, and those collectively make up the substrate for what is commonly known as epigenetics. And it's a very, very complicated story that entire textbooks have been written about. I want to bring it down to a very simple paradigm for you here, and that is, I like to think of a gene as a light bulb. And so as you can see here, a light bulb can be either totally on or totally off. Or if you live in a fancy house and you have a dimmer, it might be anywhere in between. So for the next 20 minutes, what I'd like to think for you about is that the genes are the light bulbs and the epigenetic modifications are the dimmer. And so they actually set the intensity of the light bulb. And that is particularly true for one particular of these many, many different epigenetic modifications that can occur to our DNA, which is called DNA methylation. It is the most studied epigenetic modification, in particular in human populations. And so when we imagine this light bulb dimmer paradigm, what you can see here is a DNA, a regulatory region of a gene that is not methylated. Now, what happens when we begin to add these little chemical tags, these methylation tags, to the DNA, we are pushing that dimmer down. We methylate further, push the dimmer further down, and until we finally fully have methylated this gene regulatory region, push that dimmer down, and you can see how the light bulb goes from totally on to totally off. And so now you understand epigenetics. So, why is this so important for human health and disease? Well, if you look at these 5 young mice here, does anybody actually think they look exactly alike? Nobody. Good. Otherwise, I would have to send you to an optometrist. So you see these mice, and they're actually genetically identical, thanks to great mouse geneticists such as Janet. These mice are actually not genetically different. They're exactly identical. They're clones of each other, if you wish. But the reason they look different is that their moms were fed a different diet during pregnancy. And that diet actually, that diet actually regulates the one particular gene called agouti. And it happens that the upstream regulatory region of this gene is entirely unmethylated, so the dimmer is all the way up in these mice that are yellow. As we go over to the mice, we get more and more methylation until we end up with mice that look like this. Now, what are the kind of components of the diet that affect this methylation circuitry? It's particularly things that affect methyl metabolism, including vitamin B and others, but also things like alcohol and bisphenol A, so endocrine disruptors. This is work by Randy Turtle, which I think really has set beautifully the stage for what epigenetic is. Now, most of you would argue, I don't really care whether a mouse looks like yellow or brown, but wait what happens when you see these mice grow up. So you see massive differences, and those are solely dependent on the nutrition of the mom during pregnancy. And you see that the dark mouse stays lean and fit. The other one is almost twice as big, develops all kinds of age-related diseases, metabolic disorder, you name it. Solely dependent on the mom's diet during pregnancy. So this is really a beautiful example of what epigenetics is, because you've got an environmental impact, that being the mom's diet during pregnancy, that sets this dimmer in a particular way, and it persists in these mice for the rest of their life. So it really is the environment got under the skin, got into the cell to affect health and behavior across the lifespan. Now, there are many examples emerging from human population-based studies to say that the same is true as well. In particular, there are studies from the Dutch famine and others that show that the nutrition and the lifestyle of the mother affects the epigenome of the child, whether that is chronic malnutrition or undernutrition, or things like maternal smoking, and I will show you some example on alcohol exposure. Similar work by Michael Meany and colleagues at McGill University has shown that the quality of maternal care is associated with the epigenome of the child, in many cases, again, persisting all the way into adulthood. And of course, the closest we can get to these lovely little identical mice are identical twins in humans, and many of you might know identical twins and realize that they're not really all that identical when it comes to health, when it comes to behavior. You can see these two little cuties here. Turns out that work by many different labs has shown that identical twins do start out with fairly identical epigenomes, but as they go through life, they acquire discordant epigenomes, in particular if they happen to have been separated early in life, or in relationship to different health outcomes, including diabetes and mental health. So how do we put all of this together? In my laboratory, we really try to integrate epigenetics into a model that links it very strongly to the environment, which is what I just showed you, but we're also cognizant that epigenetics doesn't occur just in relation to the environment, but also might be linked to the underpinning genetics, and we can discuss this later. So what we're trying to do is to integrate epigenetics with environment and genetics to understand how we can provide the best healthy start to our children and prevent diseases across the lifespan. And we have been focusing over the years on two particular aspects of this. And first of all, we have been really focusing very heavily on early life socioeconomic status as a predictor of adult health. And we have been also more recently focusing on early life parental stress as a predictor of adult health. And ultimately what we're trying to understand, of course, is how do these early life environments affect childhood temperament, behavior, and trajectories in a persistent fashion. And I've been standing on the shoulder of giants. This is a large body of collaborative work. You can see all our lovely collaborators listed here. And there's nobody that has been more formative in these ideas of biological embedding than the late Clyde Hertzman, my friend and mentor, who passed away 3 years ago, way too early, who has really conceptualized, even before epigenetics was actually hitting the mainstream, that there is a biological residue by which these early life experiences that we touched upon can get under the skin and have effects on adulthood. And there are many, many different studies that speak, for example, to socioeconomic status as one of the most powerful predictors of health, not only current health, but even early life effects on later life health. One study is the famous Johns Hopkins physician study shown here, where the researchers have found that the incidence of coronary heart disease in these physicians, male physicians, is 2.5-fold higher if they grew up in low socioeconomic status compared to high socioeconomic status. And so collectively what we've been trying to do is to test the hypothesis that indeed it is the epigenetic biology that is underpinning these kind of sociological effects. And so in earlier work together with Greg Miller and Edith Chen, we have been trying to test this by assembling a cohort of healthy adults in the Greater Vancouver area. And there were essentially two groups. One group that grew up in low socioeconomic status, and the other group that grew up in high socioeconomic status. And they were mixed in adulthood so that we could minimize the risk of confounding these findings by adult SES. And we looked at a number of things. First of all, we looked at the light bulbs. We looked at the gene expression pattern. And what we found is that there are differences between folks who grew up in low early life socioeconomic status versus those who grew up in high socioeconomic status. Those were random differences. Instead, there were transcriptional gene expression differences that were reminiscent of a pro-inflammatory state that was brought about by the low early life socioeconomic status. And in fact, when we test this, as you can see on the right upper corner there, when we test this directly in these immune cells that we derive from these, that we obtain from these people, we can see that the folks who grew up in low early life SES on the left have indeed a higher reactivity of their innate immune system, of these toll-like receptors that we're testing here. Furthermore, when we test these folks, when we measure their HPA axis, we found that they have a higher output of cortisol throughout the day compared to folks who grew up in high early life SES. Moreover, when we then ask, is there a DNA methylation pattern, so a dimmer switch pattern that underpins this, indeed what we find here is that there is a very highly skewed p-value distribution indicative of an association between early life socioeconomic status and this DNA methylation pattern in these adults. Interestingly, if you look at the right panel, there's a flat p-value distribution when we look at current SES, suggesting that there's the DNA methylation pattern, these dimmers in our blood, are much more highly associated with how we grew up in the first 5 years of our life in terms of socioeconomic status than the kind of socioeconomic status we have now. So collectively, what this work really shows is that early life poverty gets under the skin to affect these dimmer switches, to affect the light bulbs, the gene expression patterns, to affect immune function, and to affect HPA axis and cortisol output. Now, this, of course, has profound implications and needs to be replicated. And we have replicated this now several times. We've also expanded this and together with my wonderful set of collaborators, shown, for example, that there is an epigenetic vestige of early developmental adversity relating to family stress. So this was work published in Child Development some years ago. More recently, this relates to what we heard earlier, these kids who grew up in these institutions in Eastern Europe. We have shown together with Megan Gunner that again there's a vestige of growing up in Eastern Europe that we can see many years later in kids who have been adopted into North American families. And so this body of work then together really is starting to bring about this picture that indeed it might be the epigenetic modifications that underpin these long-term effects of early life environments. And together with my great friend Tom Boyce, we've been starting to conceptualize this in a recent review in Developmental Sciences that really talks about how epigenetics might be at the synapse of this gene by environment interplay. Now, I want to move on to a slightly different yet related issue, and that is the how can we further use these epigenetic signatures to perhaps make a difference in the life of our children that suffer from various disorders. And we have been focusing on fetal alcohol spectrum disorders in the context of the neurodefinite NCE, that as a Canadian NCE that has been supporting us. And as you might know, fetal alcohol spectrum disorders, of course, is caused by prenatal exposure to alcohol. It is a spectrum that ranges from the very severe cases on the left here all the way to more alcohol-related birth defects. It's estimated that in Canada, there is roughly 1% of all kids have the prevalence of FASD, and it's really in many ways the leading cause of mental disorders. So we started out asking the question, do we see a signature of this disease or of this disorder in the children? And if so, how can that be used to perhaps potentially diagnose them earlier and or to understand the complexity of the disease better? And in work that we published last year, we found indeed that there were many of these dimmer switches, these DNA methylation marks that were different between kids who were diagnosed with fetal alcohol spectrum disorders and those who were not. So in a classical case control study, all the blue dots that you see up there are really associated with fetal alcohol spectrum disorder. And these are roughly 400 of the 25,000 genes appear to have some association with the disease or with the disorder. Interestingly, we can learn a lot about the biology of this because many of the genes that are differentially methylated, i.e. their dimmer switch is different between kids with fetal alcohol spectrum disorders and the controls, actually relate to genes that make sense in the context of what's known about the disorder. In particular, we found that several genes, such as DRD4 and others, were actually part of the dopaminergic system, which is crucial for brain development. Furthermore, when we then do a more fancy analysis by asking what kind of networks are dysregulated epigenetically, we find that many of these genes that are differentially methylated in the fetal alcohol spectrum models are indeed involved in neurodevelopmental processes and disorders. And I want to point out, primarily, we found linkages to autism spectrum disorder, epilepsy, and anxiety. And again, this is consistent with what we know of the clinical phenotypes, and we're hoping that this can be used to hopefully lead to earlier diagnosis of fetal alcohol spectrum disorder, which tends to be diagnosed a little later in childhood, usually. But I also think it's a blueprint for understanding neurodevelopmental disorders more broadly. And so what I hope I've shared with you today is that the epigenome indeed is at the nexus between early life experiences, focused on early life poverty and family stress, but really going back to prenatal experiences and phenotypes. We think that this needs to be looked at, of course, in the context of development and in the context of the genome, but also one of the challenges and perhaps the opportunities of epigenetics is that in contrast to genetics, there's actually tissue specificity involved in shaping these epigenetic patterns. We do think that the immune system is at one of the key players, at the key substrates that listens to the early life environments and is programmed in a way to often persist across the lifespan. Now, as we sort of have been doing all of this work, we started to, and this was really motivated by Clyde's just breadth and enthusiasm, we started to think about how can we apply all of this a little bit better to make a difference in the life of our children so that we can ensure that all our children fly and take off like this little boy here. And so together with a very talented PhD student, Mina Park, we have been actually publishing a paper in Canadian Public Policy that started to touch upon how we can translate all of this. And we've been very careful with this, our proposal, but some of the things that we think this epigenetic can do to affect child health policy is that it can potentially serve as a biomarker of early life exposure, as I just showed you, whether it is poverty, family stress, or even alcohol exposure. And by doing so, it can potentially stratify, lead to better stratification, but also be a really important aspect of precision medicine. We are very hopeful that epigenetic might be serving as a biomarker for the kind of interventions that we heard about earlier in this symposium, where we proposed that there could be epigenetic benchmarking and also potentially of interventional effects, but also potentially an epigenetic predictor of whether a child does or does not respond to an intervention. We have been starting to do this together with Kim Schönert-Reichel to look at mindfulness intervention in early school-age children. We do think that there is a potential for this kind of work to influence policy direction because for some people, having this molecular evidence, if you wish, that there are these dimmer switches, that there are these little chemical tags that are attached to our DNA as a result of particular in early life environments, really might lead to a shift in public perception. In other words, it might sort of help people to understand that it's not just in your head, but it could actually be in your DNA. And perhaps more broadly, we hope that this kind of emerging science is really helping to recognize the importance of the early years for policy makers and the public. Now, there are many challenges still to overcome. Primarily, there are some scientific hurdles. Everything I've shown you and everything that's out there in the literature is really correlation versus causality, so this is a really important aspect to keep in mind. And related to this, there's really this difficulty or the opportunity, if you wish, to translate this into knowledge, a highly biological complex concept, but perhaps even more importantly, there needs to be a lot of care to not fall into some epigenetic risk messaging that creates the idea of biological determinism. So I'm very keen to discuss this further with you, what you think about all of this. But I want to just leave you with my last slide. Oops, turn me off. Well, my last slide was, is it nature or nurture or both? Thank you very much.